Hello everyone. So welcome back to IARE YouTube channel. So today in this operating system session, I am going to discuss about the process scheduling. So under this presentation, so we will look at what do you mean by scheduling, what are the different scheduling queues are there, and what are the different types of schedulers and dispatcher and scheduling criteria. So we will discuss these topics in our today's presentation. So we go to the first topic, scheduling. So once after this presentation, the student able to understand the role of the scheduler and how its behavior influences the performance of the system, and also know the difference between IBO bound processes and CBU bound processes and how they relate to the scheduling. So these are the outcomes the students able to take away from this presentation. So let us see the first concept, the scheduling. So initially we will see what do you mean by scheduling. So with respect of operating system, we have already seen the different types of the systems, multi-programming system, multitasking and multi-user systems, right? Under this we have studied various kinds of the systems. In any multi-programming system, we have more than one ready process for execution, right? So suppose in a batch system, we have many jobs are waiting to be run. And if you consider a multi-user system or multitasking system, we have many users concurrently trying to use the system, computer system. Here, the scheduler, which is a program, it will decide who to run next, which process has to run next. So this process of choosing is nothing but scheduling. So we have already seen in previous presentations the different process states. So we will come to know a scheduler will placed in between of ready state to running state, right? So this scheduler will pick the process is nothing but the decision is nothing but scheduling. Right? So next we will see, is scheduling important? Why are we required any scheduling? Some scenarios, this scheduling may not be certain in certain scenarios. So what are the scenarios are in early systems? If you talk about of the batch systems, so all the way, because we have to execute number of jobs at a time. So in that batch systems, scheduling may not be important. The algorithms also very simple. So there we will run next on tape or next on punch tape. So this in these places we are not that much bothered about our scheduling. Only one thing to run is simple pieces, only run a word processor and simple embedded systems, TV remote control, washing machines, etc. In all these systems, the scheduling is going to be not so important, right? So it is most important in which scenarios the scheduling is most important. We have seen that to utilize the CPU in an effective manner. So we already know that CPU is nothing but the processing time, right? So if you want to utilize the CPU very effectively, So we came to know that multi-user system, multi-programming system, multi-tasking system or multi-user system, right? In such a kind of system, suppose, for example, email daemon takes 2 seconds to process an email and user clicks button on application. In multitasking applications, if you take an example, email daemon takes 2 seconds to process an email, user clicks a button on application. Here the daemon is nothing but the background processes which are continuously running in a operating system, right? Continuously running in a system, and it will provide some request, right? These are nothing but daemons, right? So here email and user clicks are 2 applications are running. In first scenario, we run a daemon and then application. So here system appears really sluggish to the user, right? So in scenario 2, first run the application and then daemon. Here this application is really responsive, right? Small email delay is unnoticed here, because in what way actually the process or CPU is executing an applications in a system, it decides the performance of a system, right? So in those kind of the system where multi-user or multitasking in multi-programming systems, so the scheduling is one of the most important aspects. So this scheduling decisions, what actually this scheduling decisions will affect the performance of the system, in what way you are executing the applications. So it will affect the performance of the system. This scheduling not only affect the performance of the system, it can also affect the correctness of a system with deadlines. So with this information, what did we understand? We understood scheduling is most important concept. So while doing any application pick from ready state to running state, this scheduler is taking a crucial role. So now let us see what kind of the applications. So the application behavior. So there are 2 kinds of the applications which are bounded as CPU bound processes and as well as IBO bound processes. Let us see. So here, if you observe this application, so for the first application, because we already discussed in multi-programming system, multiple applications are executing or running parallelly. So one application is having long CPU burst. Like that, it is trying to acquire the CPU for execution. And like this, these all are long CPU burst. So when actually while in the execution is going on, it may wait to complete the execution of a task. It may wait for an IBO event or input output events. So suppose second scenario of the applications are short CPU burst. These are different applications. Short CPU burst while the time is going on in a timeline. So here these are the 2 different kind of the applications we may see in our system. So burst of the CPU usage is alternate with periods of IBO wait. So let us see the first application, CPU bound process. Suppose when a process is going to be set to be CPU bound, means that a process executes, process spends more time on CPU. More time on CPU execution. That is nothing but those processor we are going to say CPU bound process that only spends most of its time in computing or executing. This kind of the process we call it as CPU bound processes. So the time completion largely determined by the received CPU time. Like when the application is CPU bound process, then actually the time completion will be based on how actually the CPU will be received CPU time, right? So here, this also long CPU burst. This application long CPU burst like this, right? So another kind of application, input output bound process. So earlier what I said, a process, when we are going to say input output bound process, means that a process which spends more time towards more time towards input output operations. Input output operation. What are that input output operations? Read, write. These are different input output operations, because we required, suppose when a process is going to be say IBO bound process, it spends most of its time waiting for input output operations to complete. Small burst of the CPU to process input output and request for next input output while an application is going on, smallest CPU burst times, right? So it will be wait for the input output is more. That process we are call it as input output bound processes, right? So with this, when actually the scheduler, when actually scheduler has to be placed. So the observations are, generally technology increasing, CPU speeds are much faster than IBO speed. Because if you observe that now, Intel processor, Xeon processor, so many processors recently came up in a picture with largest speed, right? When technology is increasing, CPU speed is faster than IBO speed, and the CPU burst become shorter. IBO waiting is relatively constant. These are the observation with the real world scenarios. The processors are becoming more IBO bound. So we need a mix of CPU bound and IBO bound process to keep both CPU and IBO systems busy, right? So while we have to maintain concurrence and sync with the different speeds between of different devices, we need a mix of CPU bound and IBO bound process to keep both CPU and input output system busy. So the process can go from CPU to IBO bound or vice versa, IBO bound to CPU in different phases of the execution, right? So we will recommend a mix of, it's not like purely CPU bound process and it's not purely IBO bound process is going to come for the execution. We need a mix of the CPU and IBO bound process. So the key insight here is, the scheduler has to choose to run an IBO process delays the CPU bound process by a very little. The main key insight is choosing to run an IBO bound process delays a CPU bound process by very little. Suppose if you choose to run a CPU bound process, what will be happen? Prior to an IBO bound process, it delays the next IBO request significantly, right? So vice versa, if you choose an IBO bound process, it delays the CPU bound process by very little. Choose to run CPU bound process prior to IBO bound process, it delays the next IBO request significantly. So, right? Here it is very little, but here waiting time is very significant time. So, no overlap of the IBO waiting with the computation, and results in device are not as busy as possible. So that what we are generally favor IBO bound process over CPU bound process. Generally, we will favor, initially we will give IBO bound process over CPU bound process. But it vice versa, based on the CPU, based on the CPU execution. Based on that, we will select the scheduler will pick the process. Now, we will see when actually this scheduling is performed. We already have seen in before session process state. So, when actually scheduling will be placed, when a new process is created, when actually new process will be created. So, where the program is in a secondary memory, store in secondary memory and start for the execution, that time the process will be created. Run the parent or the child. That time the scheduler has to perform. So, the another scenario, process is exist and process is sitting in the new state or ready state, and then process is sitting in the ready state. Then the scheduler will be performed, who will be picked from the ready state. That time also we need to take scheduling decision. So another scenario, a process waits for the IBO. A process waits for the IBO. If you observe that in process state, new, ready, running and terminated. And then while in the running, if the process is requiring IBO operations, then it will sit in the waiting state, right? Right? So this already we have seen in a process state diagram. So here a process waits for the IBO. That time the scheduling has to be performed. Who runs the next, right? Who runs the next? And once the IBO completion, it will sit again back in the ready. That time also scheduling. A process blocks on a lock. So suppose by putting a lock, then who will runs the next? The lock holder. So that time also scheduling will be performed. And in IBO interrupt occurs. Who do we ratio? The interrupt process or the process that was waiting. So, or a timer interrupt, right? So, these are the different scenarios. The place scheduling has to be performed. Scheduling has to be performed. Generally, a scheduling decision is required when a process can no longer continue or when activity results in more than one ready process. More than one ready process. These are the different scenarios. We have to take a decision of scheduling decision, right? So now let us see. We already know that what do you mean by scheduling? When actually the importance of the scheduling, when scheduling has to be performed in whatever the scenarios, scheduling has to be performed. So the next, scheduling queues. So the operating system will maintain different scheduling queues to maximize the CPU use, right? So our ultimate aim is always we want to keep the CPU busy so that we will improve the performance of the system, and not only in performance, correctness, so many other factors we can able to improve, right, if you keep the CPU busy. So here to quickly switch process onto CPU for a time sharing system, right? So in those scenarios, the scheduling has to be taken place. Then this process scheduler will select the available process. Available process means that the processes who are sitting in the ready queue. If you observe that the processes who are sitting in a ready queue, right? It has to select among available process for next execution on the CPU. So to maintain that, it will maintain the scheduling queues of the processes. Scheduling queues of the processes. The first is job queue. Second is ready queue. And third one is device queue. If you observe in the process state diagram, so here it is maintaining the queue. This is job queue. Here, this is ready queue, because I already said in process state diagram, each and every state also is having of their own queues, because it's not like one process only in such a state, right? So the other process who are ready for execution, they will be sitting first queue and then come into this state. And here device queue. So these are the different queues are available and able to maintain by the operating system. The job queue set of all processes in the system. So where it is there? In the secondary memory. This job queue will be maintained in the secondary memory. So the ready queue set of all processes residing in a main memory, right? Because once we are saying the program is a process, means that it is ready for execution and it is sitting in the main memory. Then only we will say that it is in execution, right? It is ready for execution and ready and waiting to execute. So this process, the ready queue process, will sit in the main queue. And now the next device queue, the set of processes waiting for an IARE device. So when actually while in the ready state, the process is in execution, it may require some input-output operations. That time it will go in wait in the waiting state. That time here it will maintain the device queue. Right? Now these are the three scheduling queues. So let me see the representation of the ready queue and various IARE device queues. And as in the before presentations, each process is maintaining their own associated PCB, process control block, right? So here the queues functionality will work like this. In ready queue, the first process, the queue header and tail, and each it is associated with the the corresponding process control block, and like this, actually in the queue header, the head is maintaining of the address of the process control blocks, and tail is maintaining the last, right? So in magnetic tape unit 0, like this, the ready queue and various IBO device queues will be represented in a operating system, right? So now let us we move to the next topic, types of the scheduler. Types of scheduler. So here a process will be migrate from one process to another. A process will migrate from one queue to another queue before going to be in a terminate, right? So while a process is migrates from one queue to another queue, different types of the schedulers will be present, and which kind of scheduler and what kind of the responsibility of the schedulers. So the scheduler, we already know that it picks an appropriate process from these queues to maximize the CPU utilization. What are the types of the schedulers? Different types of the scheduler: long-term scheduler, short-term scheduler, and medium-term scheduler. These are the three different schedulers will be present. Scheduler is not nothing but a program. Please remember that. It's not a separate device, right? It is a program which will be resided in your operating system. So now let us move to the first kind of scheduler, long-term scheduler. This long-term scheduler or process scheduling, this scheduler we will call it as sometimes process scheduling, sometimes call it as job scheduler. There are two words, long-term scheduler or job scheduler, right? This long-term scheduler will pick the process from the mass storage device such as a secondary memory, hard disk, right? And places it in the ready queue, that is in the main memory. So if you observe here, where actually the long-term scheduler will be sit here. It will pick the process from memory, secondary memory, and make it available in the ready queue. In the ready queue, that is in the main memory. That is a long-term scheduler duty. So what it will do? It will control the degree of multi-programming. What do you mean by degree of multi-programming? It controls degree of multi-programming. So which scheduler? The question will come, objective questions will come like this. Which scheduler will control the degree of multi-programming? So the answer is long-term scheduler. So what do you mean by degree of multi-programming? Means that the number of programs are ready to get or going to keep, make it available in the ready state. So that is nothing but degree of multi-programming. So the next scheduler is short-term scheduler. Another word is CPU scheduler. Another word is for long-term scheduler. Another word is job scheduler. So here short-term scheduler. Another word is CPU scheduler also. So here this CPU scheduler, if you observe in the process state diagram, the CPU scheduler will be placed from ready state to running state. From ready state to running state. CPU scheduler. Right? So the CPU scheduling decisions will take place when a process is sitting in the ready state. It will switches from running state to waiting state and switches from running state to right. So the CPU scheduling decisions will take place in various places. It switches from running to waiting state and switches from running to ready state, running to ready state, running to ready state and switches from waiting to ready state and then terminates. Right? So here we have to talk about of the two kinds of the scheduling will be placed inside the short-term scheduler. The first one is non-preemptive scheduling and another one is preemptive scheduling. So non-preemptive means that you are not able to forcibly take away the CPU from a process. Right? So the scheduling 1 and 4, because in this scenario, if you observe that running state to waiting state, when the process voluntarily, if it requires IBO operations, then only it will go into the waiting state. Here we are not forcibly take away the CPU from a process. And when a process is going to be terminated. This kind of the states, the scheduling is nothing but non-preemptive scheduling. Non-preemptive means itself not forcibly take away the CPU from the execution. So the other scenarios is call it as preemptive scheduling. When actually preemptive scheduling is going to be happen means that when interrupt is going to be occurred, when it access to shared data and preemption while it in a kernel mode, So in these three scenarios, the scheduling is going to be considered as preemptive scheduling. That when interrupt occurs, what we are doing, when high priority process comes, then the low priority process, based on the priority, we are saving the state of a process and then hand over the CPU to the highest priority process, right? That type of scheduling is nothing but preemptive scheduling. So let us see the preemptive versus non-preemptive scheduling. In non-preemptive scheduling, once a process in the running state, it continues until it completes. Blocks an IBO or voluntarily, if you observe that the word voluntarily means that the process itself wants to go and sit in a waiting state. That time only non-preemptive scheduling will be happen. So a single process can be monopolized the entire system. So now come to the preemptive scheduling. The current process can be interrupted by a OS. When an interrupt will be come in the picture, the high priority process, or suppose if some system program has to be executed immediately, and then that time actually it will rise an interrupt and move to that process is moved to ready state, because running state to ready state, it will go back into the ready state, right? That time means that we have forcibly taken away the CPU. So usually after a timer interrupt, Because we have already observed, and even in the next session we are going to study the round robin scheduling algorithm, because each and every process is having a certain time quantum to maintain and to give it a feel of interactive scheduling. So for that we are maintaining timer, right? So whenever timer interrupt and process exceeds this time limit, that time also it will go automatically from running state to ready state, right? So that in that scenarios, and ensures fairer service as a single process, because we already say that in non-preemptive the single process is monopolize the entire system, because it's not good, right? Because one person is not like that entire CPU is using the entire CPU execution by himself. So then there is no meaning of interactive, right? So fairer service at the time, the preemptive scheduling must be required. It requires a timer interrupt. So let me see the question kind of thing, the difference between preemptive and non-preemptive scheduling. So we will consider these are the parameters. What is actually basic concept of preemptive and non-preemptive, and interrupt, starvation, overhead, flexibility, cost, and CPU utilization. In these parameter scenarios, how actually preemptive and non-preemptive scheduling will be work. So in this, the resources, preemptive scheduling, the resources is here CPU cycle are allocated to the process for a limited time, in a preemptive scheduling. Under non-preemptive scheduling, once the resources are allocated to the process, so the process holds the CPU until its completion, right? So now under category of interrupt, the process under preemptive scheduling, the process will be interrupted, right? Under non-preemptive scheduling, the process cannot be interrupted. The process voluntarily, or once the completion of execution, then only it will go into the terminate state. So now starvation. Starvation means that a process, a higher priority process will come and take away the CPU. So a process which is having a less CPU execution time will wait in a longer time to get the CPU. That is nothing but starvation. It is starved to acquire the CPU. Suppose if a process is having low execution time, still it has to wait longer time when high priority process comes, right? If a process having high priority frequently arrives in the ready queue, then lower priority process is going to be starved. Under non-preemptive scheduling, is this starvation will be happen? No. So this starvation, if a process with a long burst time is running the CPU, then later coming the process with less CPU burst time may starve. In that scenario only, under non-preemptive scheduling, the starvation is going to be happen, right? The overhead is nothing but switching from one process to another time. The time between switching from one process to another process. It has the overheads of scheduling the processes, right? See, one transition from one process to another process. So here we don't have much overheads, but preemptive we have overhead, right? So flexibility, it is preemptive scheduling is very flexible, and non-preemptive is rigid because it is not going to give away the CPU. The cost will be associated here. The cost is means that execution time, the turnaround time, throughput, and this cost is associated with this. And here no cost will be associated with this scheduling. CPU utilization, preemptive scheduling, CPU utilization is high. It is low in non-preemptive scheduling. So here, what kind of scheduling has to be taken? Consider it also. You have to take decision based on what kind of the system. right? Suppose if it is batch system, you have to consider a non-preemptive scheduling, right? If you are time sharing systems, right, that moment actually preemptive scheduling kind of the scheduler is best. So now let us move to the another scheduler, another type of scheduler, medium term scheduler. Usually most of the textbooks have given the long term scheduler and short term scheduler. So some textbooks has given the medium term scheduler. So this medium term scheduler removes the partially executed process from the ready queue. It will remove the partially executed process from the ready queue, so that actually it will reduce the degree of multi-programming. This process can be later reintroduced in ready queue. If simply sitting in a ready queue, it means that it will increase, right? This medium term scheduler duties, it will take away the process from the ready queue, so that it will try to reduce the degree of multi-programming. And also they can resume this execution from where it is left off. This procedure also referred as swapping, swap in and swap out. That moment actually the medium term scheduler will be in a key row. So now let us see the comparison among the schedulers. Long term scheduler, short term scheduler, medium term scheduler. So long term scheduler, it is a job scheduler. Another word is a job scheduler. Another word is for short term is CPU scheduler. Another word for medium term is swapping scheduler. Right? The speed is lesser than short term scheduler. Speed is fast because execution speed. Speed is in between the both short and long term scheduler. So the long term scheduler controls the degree of multi-programming. So the short term scheduler provides lesser control over degree of multi-programming, and medium scheduler, it reduces the degree of multi-programming. So the another comparison is with the long term scheduler, it is almost absent or minimal in time sharing systems. So the short term scheduler will be present more effectively in the time sharing system. So the medium term scheduler, it is a part of the time sharing system. So come to the under long term scheduler, it selects the process from pool and loads them into the memory for execution. So here in short term scheduler, it selects the process which are ready to execute, and then medium term scheduler, it can reintroduce the process into memory and execution can be continued. Right? This is a comparison among the different kind of the schedulers. Now let us move to the next topic, dispatcher. So dispatcher is nothing but it's a program or it's a module which gives the control of CPU to the process selected by the short-term scheduler. And this involves, because we already informed that the context switches will be happen from one process to another process. Here we already said short-term scheduler will select a process from ready state to running state, right? That is a place. There this dispatcher will be taken care and control the CPU to the process selected by the short-terms, move in and move out while doing the swapping, switching to the user mode. In those scenarios, this dispatcher will take control of the CPU. And jumping to the proper location in the user program. to restart the program. We already said that when actually switching is going to be happen between one process to another process, it will save the state. So this dispatcher will be responsibility is will jump to the correct location, because in this module it has a current address instruction where it is ended. So this dispatcher will be go and directly take away from which state onwards, right? So the dispatcher duty is it gives the control of the CPU to the process. Control of the CPU to the process selected by the short-term scheduler. Right? So while this CPU is going to be allocated to the process, that span, the short span, we call it as dispatch latency. The time it takes for the dispatcher to stop one process and start another running. Right? See, if you observe here, ready and running, right? Scheduler or dispatcher. Scheduler will pick the process from ready state, to whom actually I have to give the CPU. So the dispatcher will hand over the control of the CPU to the particular process, right? So while it moves from one process to another process, the time gap is nothing but dispatch latency, right? So that is nothing but dispatcher. That is about a dispatcher. So now let us look at the another scheduling criteria. These are all the concepts which will be helpful for our scheduling algorithms, right? So this is a basic fundamental concepts we required to decide which scheduling algorithm is going to apply, right? So the scheduling criteria to select a scheduling algorithm is, these are the different parameters we have to consider: CPU utilization, throughput, turnaround time, waiting time, and response time. These are the different parameters we need to consider while doing scheduling. So the first one is CPU scheduling. Utilization. CPU utilization. It keep the CPU. What do you mean by CPU utilization? Means that always we are trying to keep the CPU as busy as possible, right? So this is one of the criteria while pick any scheduling algorithm. The another one is throughput. Throughput is nothing but the number of processes the complete per their execution per time unit. Throughput is nothing but the number of processes completed their execution per a time unit. That is nothing but throughput. So now next parameter is turnaround time. Turnaround time is nothing but when a job is going to be submitted, the difference between of job submission and job completion. The difference between of the process submission and then process completion. Because we have already seen that with the short-term scheduler, so it's not like a CPU is once it is allocated, it is continue with the particular process, right? It have different process will be executed under multi-programming environment. The turnaround time is the most crucial parameter, the amount of time to execute a particular process, or in other words, the difference between of the process submission and process completion is nothing but turnaround time, right? The waiting time, the amount of time process is waiting in the ready queue, that is nothing but waiting time. So for a good time sharing system, the waiting time has to be less or waiting time has to be high. Waiting time should be very less. It has to acquire the CPU as early as possible once it is coming in, sit in the ready state. So the response time is nothing but the amount of time it takes from when a request was submitted until the first response is produced, not output here for time sharing environment. That is nothing but response time. Because once a process is putting a request, I need CPU. That when actually the CPU is responded, I am ready for your execution. That's nothing but that time is nothing but response time, right? So these are the different parameters we have to consider while select a scheduling algorithm. So these are the different references I have used for my. So the most of the first textbook is the Calvin book, Tannenbaum, and William Stellings. So these are the three authors have written wonderful and very good explanation about our operating system, all concepts. Right? Thank you so much.
Like, share and subscribe. Hit the bell icon for more updates.